Series of numbers are about the question whether it is possible to add infinitely many numbers and still get a finite result. That question had actually stumped the Greek philosophers that founded mathematics more than 2,000 years ago, because they were of the opinion that if you sum infinitely many quantities, then the sum must be infinite, and that actually turns out not to be true. However, you need limits for a stand-in for an infinite sum, because if we really want to look at the definition of a series, we will realize that no, we don't sum infinitely many quantities. We are using a limiting process. Aside from that, certainly we also would like to know why we would want to sum infinitely many numbers, and that will certainly be answered in following presentations, as well as also briefly in the introduction here. Let's take a look at, I think, the question first. So, is it possible to form an infinite sum of positive numbers and get a finite result? Well, here's the geometric answer. Take a 1 by 1 square and cut it in half. That means this area is 1/2. Cut the rest in half. This area is 1/4. Cut the rest in half. This area is 1/8. Cut the rest in half. This area is 1/16. Cut the rest in half. This area is 1/32. And so you can see that we can add all those numbers up, and we end up with a sum 1/2 plus 1/4 plus 1/8 plus 1/16 plus and so on indefinitely. And yet we can also see geometrically these tiles are filling up the whole square. They're not going to reach this one point here, but that one point at the top right corner has area 0, which means the sum of these numbers should be the area of the square, so that sum should be 1. So if we want to have a quick answer to the question, can an infinite sum of positive numbers be finite? This answer says that the question is yes. That the answer is yes. Okay, so the more important questions then are, how would we do this in general, and why would we want to do it? And I think I first want to talk about what these infinite sums could be good for. So one thing that is rather surprising, and that is something that we will also talk about when we talk about geometric series, is that infinite decimal numbers actually are infinite series. Taylor polynomials that you have seen earlier in calculus are finite sums that can be used to approximate functions, and so now the question becomes, if we talk about infinite Taylor polynomials, and we will talk about that when we talk about what is called power series, would that be equal to the function? And the answer is sometimes, and we'll talk about that in a later presentation. Infinite sums of functions can also be used to represent other functions in quite a few areas of applied mathematics. Typically, you have a family of functions that you understand reasonably well, or a family of functions that is particularly appropriate to a certain context, and you try to represent everything else as an infinite sum of functions of that type. Finally, in certain statistical experiments, every positive integer is assigned a probability, and the infinite sum of these probabilities must be 1, because the total probability of all the outcomes must be 1. So these are the applications, and this idea will be investigated more deeply in statistics classes. And we could also simply say, if you like an intellectual challenge, then infinite sums certainly qualify. And the reasoning that we need to talk about convergence and divergence of infinite sums requires a good bit of pattern recognition. It requires some working with inequalities, which is helpful, as well as some logic, because we will have to make sure that all the implications go the right way. And so that would be an intellectual challenge, and as I would always want to say, we want to face challenges rather than avoid them. So, what should an infinite sum be? Well, that definition is going to be a little lengthy, but let's just get started. Definition, we take an infinite sequence. That's what we want to add up, all these numbers a in here. Then the expression sum n equals 1 to infinity a n is called an infinite series. And for k greater or equal than 1, the kth partial sum pk of the series sum n equals 1 to infinity a n is defined to be pk being the sum n equals 1 to k of the a-n's, or a1 plus a2, not a1 plus all the way through ak. Let me fix that real quick. There, now it's A2, so the partial sum is nothing but the sum of the first k terms. And if this sequence of partial sums pk, k going from 1 to infinity, converges to the number s, then we say that the series sum n equals 1 to infinity is convergent. And we will write, and that continues over here, we will write that the sum n equals 1 to infinity an is equal to s, which is the limit as k goes to infinity of the partial sums, or that a1 plus a2 plus all the way through an and so on is equal to that limit s. The number s is also called the limit, or more commonly the sum of the series. And if the sequence of the pk's diverges, then we will say the series sum n equals 1 to infinity an is divergent. So when we look at these symbols that literally denote infinite sums, and what we actually always have to keep in mind is that what we're actually talking about as we are working with this stuff is actually the sequence of the partial sums, and we talk about still about convergence of sequences. For starting indices other than 1, the corresponding definitions are similar, so you can have a series that starts at 2, starts at 3, starts at 0. Starting points of 0 and 1 are the most common ones. As a visualization, well, if we were to visualize a sequence in the function picture, which I don't necessarily like all the time, but here it works rather well, then the sequence would just be a function from the integers to the real numbers, and so it would just be a function that outputs these blue dots, and there is nothing else. This is the graph of the sequence. The series now is what we can visualize if we take advantage of the fact that the length of these intervals here is 1, because now the first term would be the area, the first term of the series would be the area of this rectangle, the second term would be the area of this rectangle, the third term the area of this rectangle, and so on, and so on, and so on. And that basically says that the sequence gives the points n, the blue points that we have seen up here. And the series gives the sum of the areas of the rectangles if such a summation is possible. Let us start with some series that are really very, very important, and that is geometric series. And here's a theorem: when the number q is between -1 and 1, then the sum of the geometric series is the sum n equals 0 to infinity q to the n 1 over 1 minus q. And for all other values of q, the geometric series diverges. Okay, how do we prove that? Well, we look at q being between -1 and 1, and we use a summation formula. The sum n equals 0 to infinity q to the n is, of course, the limit as k goes to infinity of the sum n equals 0 to k q to the n. And for this summation here, there is a formula that we can look up, or some of you may even have it in memory. That sum is 1 minus q to the k plus 1 divided by 1 minus q. So this is the limit as k goes to infinity of 1 minus q to the k plus 1 divided by 1 minus q. And now with q being between -1 and 1, these powers here go to 0, and that means that the limit is 1 over 1 minus q. For all other values of q, the geometric series diverges. Well, when q is less than or equal than -1, or q is greater than 1, we have that the summation is still 1 minus q to the k plus 1 over 1 minus q, and that means when q absolute value is greater than 1, then this thing here goes to infinity, and so the series itself goes to infinity, because you'll have a negative divided by a negative, so it goes still to plus infinity. And for q equal to -1, you get that this term here oscillates between plus and -1, and that means that you have a sequence that diverges because it oscillates. Finally, and that's because q to the k equals 0 to infinity, diverges. And finally, for q equals 1, well, for q equals 1, the sum of q to the n is just k plus 1, and that diverges because k plus 1 gets larger and larger and larger. Okay, so the important part here then is that for the right values of q, we have not only that the geometric series converges, but we also know the value of the geometric series. And that means after some more algebra, we will be able to compute values, which is nice. So if you have two convergent series, sum an and sum bn, and c a real number, then the sum of the an plus bn, the sum of the an minus bn, the sum of the c times ans, and a shifted series where you use your starting index to be 1 plus m, and your index is shifted with a j minus m here, these series converge too, and their sums are, well, the sum of the sums of the terms is just the sum of the individual series. That comes straight from the limit laws for sequences. The limit of a sum is the sum of the limits. Similar for differences, the sum of a bunch of difference is just the difference of the sums. The sum of constant multiples is just the same constant multiple times of the overall sum. And finally, if we're looking at these numbers here, it starts with j equals 1 plus m, but when j is equal to 1 plus m, then j minus m is 1. So this is a summation that starts at 1 and then goes to 2, 3, 4, and so on, which means that this summation really is just nothing else but the sum n equals 1 to infinity of the ans. This kind of shifting will be important every so often to make sure we can apply the right formulas, and we're going to see that, in fact, in the next example. Namely, if I want to compute the sum of the series sum n equals 0 to infinity, 1 over 3 to the n plus 4 to the n plus 1 divided by 7 to the n plus 2, then looking at this we can see that that does look geometric in some ways. It's just that some of the indices are off and we've got two terms rather than one. So if we just use the algebra laws from the previous panel correctly, we ought to be able to compute that. So let's go. Here's the sum. And the first thing I can do is realize that this is the sum of 1 over 3 to the n plus the sum of 4 to the n plus 1 divided by 7 to the n plus 2. Now the sum of 1 over 3 to the n, that's just the sum of 1/3 to the n, which is geometric, so that's fine. This sum here, well, this sum has exponents that are different from each other, so I would probably want to factor a 7 out of the denominator. So I get the first sum to be the same, plus 1/7 times the sum n equals 0 to infinity, 4 to the n plus 1 over 7 to the n plus 1. If I look at this, well, the first one is still okay. The second one, if I want to apply the formula for geometric series, I would like to have a 4 to the n and a 7 to the n, not a 4 to the n plus 1 and a 7 to the n plus 1. So I can factor out another 4/7 here. So now I've rewritten the first one. 1 over 3 to the n is 1/3 to the n. Good. The other one is 1/7 plus sum n equals 0 to infinity 4/7 to the n plus 1, which is the sum 1/3 to the n plus 1/7 times 4/7 times the sum n equals 0 to infinity 4/7 to the n. And now this one, as well as that one, fit the pattern of sum q to the n with q between -1 and 1. So the first one is now 1 over 1 minus 1/3, and the second one is 1/7 times 1 times 4/7 times 1 over 1 minus 4/7, and so that would be 1 over 2/3, which is 3/2, plus 1/7 times 4/7 times 1 over 3/7, which is 7/3. So that's 3/2 plus 4 over 21. And 3/2 is 63 over 21 plus, wait. 3/2 is 42. Hang on, so that's, come on. Okay, 3/2. The common denominator, goodness, fractions. Ultimately use a calculator if necessary, but as I always preach to people, you ought to be able to work your fractions, so I ought to be able to do that too. Common denominator is 42, so 3/2 is 63 over 42. 4 over 21 is 8 over 42. 63 plus 8 is 71, so this is 71 over 42, and that ends this computation. Now, let's remember that I said that decimals are actually series, and that is because any decimal we have independent of how long it is actually equal to the number before the decimal point plus first decimal digit divided by 10 plus second decimal digit divided by 100 plus third decimal digit divided by 1,000 plus fourth decimal digit divided by 10,000, and so on and so on and so on, potentially indefinitely. And if there is no pattern in the decimal digits, then the number is irrational, and we cannot do much other than write down the number as far as we have digits. For a function that, as this one here is supposed to be, where the ... indicates that this just continues as 5151 indefinitely, well, we know that repeating decimals are rational numbers, and we know that rational numbers are fractions, which means we ought to be able to convert this into a fraction. So let us take this number 3.51 bar, as it's also often written out, is 3 plus 51 over 100 plus 51 over 10,000 plus 51 over a million plus and so on, right? It's always a 51 divided by the next higher power of 100 because we've got two digits grouped to each other. So this is 3 plus 51 over 100 to the first plus 51 over 100 squared plus 51 over 100 cubed and so on, which is 3 plus 51 times the sum n equals 1 to infinity 1/100th to the n. This looks geometric, but the starting index is not the right one. So now we need to shift the index here. And to do that, we remember, of course, there's a 3 out front. This is 51 times the sum k equals 0 to infinity 1/100 to the k plus 1. So we simply set that n is supposed to be k plus 1, and when that happens, then k is n minus 1. So when n is equal to 1, k is 1 minus 1, which is 0, which gives us the right starting point. Well, now we have a k plus 1 in the exponent rather than a k, so we factor out a 100. So we get 3 plus 51 times 100th times the sum k equals 0 to infinity 100th to the k. And now we can use our formula for geometric sums on this infinite sum. So we get 3 plus 51 hundredths times 1 over 1 minus 100th. 1 minus 100th is 99 hundredths, so this should be, after you work out the reciprocal, 100 over 99. So this is 3 plus 51 hundredths plus 100 times 100 over 99, and that is 3 plus 51 over 99, and 3 is 297 over 99, so this should be 348 over 99. And so that means we can convert this repeating decimal, and with the same principle, any other infinite repeating decimal, into a fraction. And yeah, if you simplify that fraction, I apologize for not doing that, but yes, once you have a fraction, you ought to see if it simplifies. And 99 divided by 3 is 33, and if you divide 348 by 3, you get 116, and now there are no more common factors. All right, theorem. Well, the limit test for divergence. Essentially, the situation with series is very unfortunate in the sense that there are very few series like the geometric series for which we actually can write down the answer, for which we can actually write down what the number is. And so the next best thing is then to determine whether a series converges or diverges, and we first want to rule out the most trivial way in which a series can diverges, and that is what the limit test does. Namely, if an, sum n equals 1 to infinity an, is a convergent series, then the limit of the terms must be equal to 0. And that is a test for divergence, because if the limit of the terms is not 0, because either the limit doesn't exist or because the limit is something other than 0, then the sum cannot converge. The proof is actually pretty simple. Suppose for a contradiction that the an's did not converge to 0, then there would be a finite epsilon greater than 0, so that for any n there is a capital N past that for which the capital Nth term is greater than epsilon. But that means either the partial sum p sub n or the partial sum p sub n minus 1 is farther away from the limit L than epsilon over 2. Either Pn minus 1 is farther away, or if Pn minus 1 is closer than epsilon halves, then this jump by epsilon will either bounce it through the limit or bounce it in the other direction, but either way, it'll push it farther away than epsilon halves from the limit. And remember that a sequence is only convergent when all the terms eventually get arbitrarily close to the limit. And here we have a threshold epsilon halves that every so often is violated. Okay, so because this can happen for arbitrary numbers n, that there is a later term in the partial sequence of the partial sums that is farther away from L than epsilon halves, because this can happen arbitrarily deep into the sequence of the partial sums does not converge to L, and that's a contradiction, and therefore the AN must converge to 0. And that is the limit test for divergence. As a visualization, well, if you have a sequence of positive terms and the terms always stay above 0, then you can see that the total area here, if this goes on indefinitely and stays away from 0, would be an infinite area here. And if you have something that bounces, then even though this area plus this area will be 0, this area plus this area will be 0, you will always have that the partial sums oscillate here between -1, 0, -1, 0, -1, 0, and that also does not stabilize anywhere. That also doesn't have a limit. What we therefore then want to look at in terms of examples, well, the series of a bunch of terms that are 1 that diverges, and that's because the limit of 1 is 1, which is not 0. The series of alternating terms, -1 to the n, diverges, because the limit as n goes to infinity of -1 to the n does not exist, and so in particular the limit cannot be equal to 0 if it doesn't exist. And those are, again, just fairly simple examples. What you want to be really careful with, however, is that just because the terms converge to 0 does not mean that the series has a finite sum, and that is where we are headed next. And to be able to prove this fairly quickly for these so-called p-series, we first introduced the integral test. The integral test says the following: if f of x is a non-negative, non-increasing function, then we consider the series sum n equals 1 to infinity f of n, and that series converges if and only if the improper integral from 1 to infinity f of x dx converges also. So this means if the series converges, then let's reason from the integral point of view. If the integral converges, then the series converges, and if the integral diverges, then the series diverges. That is easily visualized, so the idea for the proof is that here you have your function, and for this sequence of pictures, let's assume that the integral converges. Of course, you can't see that from a finite picture, but I'm trying to indicate it here by this thing decaying very rapidly. And on the horizontal axis, I've got n or x, right? So here's the interpolating function. Here's f of 1, here's f of 2, here's f of 3, f of 4, f of 5, f of 6, and those are the terms that are being summed in the series. Well, then the series itself is the area of this rectangle plus the area of this rectangle plus the area of this rectangle plus this area plus this area plus this area, and so on indefinitely. And if the integral converges, that means that the area underneath the function is finite, and that means that the area of the net area of all these rectangles must be finite also, and that means that this series has a finite sum. You would, in an abstract argument, actually have to invoke the monotonic sequence theorem, but this is the idea. If we now look at the situation, what happens when the integral diverges? Well, when the integral diverges, again, this picture is not indicative whether the integral diverges or not, but I tried to bump it up a little bit to say that there's a lot of area here. Then we still have the same idea. We have that our sequence just evaluates the function at integer points, but this time I just draw the rectangles a little bit differently. Certainly this is also a rectangle of area f of 1, this is a rectangle of area f of 2, this is a rectangle of area f of 3, and so on and so on. And now here we can see that the net area underneath these rectangles, which is supposed to be the sum of the series, this net area contains the area under the function. and if the improper integral diverges, then the area under the function is infinite, and that means that the net area of these rectangles is also infinite, and that would mean that the series diverges. Okay, so even though integrals certainly are hard, if you can integrate the expression that gives the term of the series, you can determine if the series converges or diverges, and you ought to do so. In terms of situations in which that is possible, we are going to, as a finishing couple of theorems, we're going to talk about p-series. The harmonic series is a very important example. The harmonic series is the sum n equals 1 to infinity of 1 over n, and that series is divergent, as we are about to prove. But note, and this is very important, its terms converge to 0. So just because your terms go to 0 does not mean that your sum will be finite. This is a mistake that has been made by calculus students for generations. Stay away from it. The harmonic series shows that just because your terms go to 0 does not mean that your series has a finite sum. In terms of a proof, well, we are just going to use the integral test, and we know that the integral from 1 to infinity of 1 over x dx, that is the limit of as t goes to infinity of the integral from 1 to t of 1 over x dx, which is the limit as t goes to infinity of the natural logarithm of t, and that is infinity. Technically I would have to say ln t minus ln 1, but ln 1 is equal to 0, so there is no problem there. So by the integral test, because the corresponding improper integral diverges, the harmonic series diverges too. Okay, so now let's generalize the harmonic series and talk about the p-series test, which says that the series sum n equals 1 to infinity converge of 1 over n to the p converges if and only if p is greater than 1, which then shows that the harmonic series, of course, is a representative of this larger family of series, and we can also see that it is the breaking point. It is where the convergence behavior changes. And we will apply the integral test. So, and because we have already taken care of p equals 1 on the previous panel, we can let p not be equal to 1. And so now if we consider the integral from 1 to infinity of 1 over x to the p dx, well, that is the integral from 1 to infinity of x to the negative p dx. And with a simple power rule, we get that that is 1 minus p x to the 1 minus p at a lower bound 1 and an upper bound t going to infinity. Now when p is greater than 1, we will have a negative exponent, and something going to infinity raised to a negative exponent goes to 0, which means that in that case the value will be finite. In fact, the value will be 1 minus p for p greater than 1. It'll be p minus 1 because it's at the lower bound. The value will be p minus 1 for p greater than 1. And for p smaller than 1, well, for p smaller than 1, we have at the upper bound a t that goes to infinity now raised to a positive number. So then the integral will be infinite. And so that means the result follows via the integral test, because for p smaller than 1, the integral diverges, therefore the series diverges. For p equal to 1, the series diverges, as we have seen, and for p greater than 1, the integral converges, and therefore the series converges, and that takes care of that. Now, note that this value of p minus 1 for the integral for p greater than 1 is not the value of the series. So some values of p-series are that the sum of 1 over n squared is pi squared over 6, the sum of 1 over n to the 4th is pi to the 4th over 90, the sum of n equals 1 to infinity 1 over n to the 6th is pi to the 6th over 945, and you may ask yourself, how do you come up with these values? The computation would actually require complex analysis, which is quite a beautiful course to take if you're interested in pure mathematics. I looked those numbers up, and for these values, for values like these, I would always want to use the following principle. If you need the number, and the number is all you care about, look it up. Very smart people have literally worked for centuries, not individually, but as generations of very smart people, to find various values of these series. So if the computation is possible, there is a chance that the number is cataloged, and so you can just find it by looking it up in the right references. If you want an intellectual challenge, especially along the lines of pure mathematics, well, then you want to compute it, but be aware that you may need additional training because this stuff can and does get rather nasty. Okay, this was our introduction to series. We now know on one hand that infinite sums can be finite. We have some prototypes of these finite infinite sums, but we also have a prototype, namely the harmonic series, that says just because your terms taper off does not mean that the sum itself will be finite. With that, I release you into your homework assignment.